Hi students, this video covers Unit 3.1, Intro to Rational Functions. So our objectives are to define a rational function, determine the domain of a rational function, and learn the key characteristics of rational functions. So a rational function is just the ratio of two polynomial functions, and again, it's key that the numerator and denominator be polynomials. We know a polynomial is an expression that has terms that have integer exponents and real numbers as coefficients. And we know the domain of all polynomials is all real numbers, or as we write it in interval notation, negative infinity to infinity. So since the domain of a polynomial function is negative infinity to infinity, when we have a rational function, the only thing that could mess that up is the denominator equaling 0. In the example that we have x squared plus 5x plus 1 divided by x minus 2. The domain is going to be all real numbers except what makes the denominator 0. And in this case, all you have to do is set that value equal to 0. We'll find that x equals 2 is the value that makes the denominator equal to 0. So our domain is going to be all real numbers except x equals 2. And there are a couple of ways to write this. I would highly recommend using the proper interval notation, but you could also have x such that x isn't equal to 2. We could have that set. I'm sorry, I don't need that. I don't need the colon. Excuse me. So we could also have x such that any value of x such that x isn't equal to 2. That works. But for a rational function, the domain is all real numbers except the values for which the denominator equals 0. So moving ahead, excuse me. So now in our first example, we're going to find the domain of these two rational functions. Some of this is going to require factoring. A lot of it is going to require factoring. So for x squared plus x minus 12, we're looking for factors of negative 12 that add to be positive 1. That's going to be a negative 3 and a positive 4. So we set those equal to 0. We get x equals 3 and x equals negative 4. So our domain is all real numbers except those two values. In interval notation, we would have negative infinity to negative 4 union negative 4 to 3 union 3 to infinity. So we just take out each one of those values and go from negative infinity to infinity with the breakpoints. For the second example, we can factor the numerator. We get, to see if anything cancels out, not for domain, we get negative x, and that will give us x squared minus 4. And that's still just divided by x plus 3 and x minus 3. So in this case, in the denominator, we're finding factors of negative 9 that add to be 0x. So there's going to be a positive 3x and a negative 3x that make that work. So we get x equals negative 3 and x equals positive 3 as our zeros for the denominator. So we're going to, why am I drawing a number line? I'm used to making a polynomial inequality. We want to say our domain is negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. And so that's the domain of those that rational function. So when we have rational functions, we of course have discontinuities. And there are two kinds of discontinuities we come across. We either come across a vertical asymptote, which is going to be represented by a factor that cannot be factored out. So if we go back a slide for a moment, we see in the denominator for both rational functions, neither binomial could be factored out by something in the numerator, and that makes that a vertical asymptote as opposed to a whole. A whole is a value that can be factored out. So for instance, we have this function, we have this graph to the right, and in the factored form is x plus 1 times x minus 1 divided by x plus 1 times x minus 3. You see at -1, we have a hole in the graph, and that's because the factor that produces -1 can be canceled out. When that happens, we get a hole in the graph. It's still a discontinuity, but it means that as the original rational function is set, you can't equal -1. But because you can factor it out, technically you can equal -1. And for an asymptote, we see at x equals 3, which is produced by the x minus 3 factor, that cannot be factored out by a term in the numerator. And so what we get is a vertical asymptote. So a vertical asymptote, the factor can't be factored out. Whole, the factor can be factored out. So for the next one, we need to classify our discontinuities. That is going to require that we factor the numerator and denominator and then classify our discontinuities. So the numerator is going to factor to be, we already have seen this, x plus 4, x minus 3. In the denominator, we have factors of -6 that add to be -1. So we're going to say x minus 3 and x plus 2. So x equals -2 is a vertical asymptote, and x equals 3 is a whole because it can be factored out by canceling. For g of x, we're going to have, so if you want to factor this the proper way, we would have 3x squared, and we're looking for factors of -6 that give us -5x. So we say 3x squared minus 6x plus x minus 2, and that factors to be 3x times x minus 2, and then we get plus 1 times x minus 2, and so we get 3x plus 1 times x minus 2, and then divided by x plus 4 and x plus 2. Oh, let's go back a slide for a moment. Let's see. So we get x equals -4. That is a vertical asymptote because it can't be factored. And x equals -2 is also a vertical asymptote because it also cannot be factored out. So nothing in the numerator cancels. The -2 and the +2 cannot cancel out. So in the case of g of x, 2 vertical asymptotes. A horizontal asymptote is if as x goes to infinity, the graph tails off to this horizontal line. That's called a horizontal asymptote. In this case, this first function has a horizontal asymptote of y equals 4. And this second function has a horizontal asymptote of y equals 2. Like if this graph was to continue to go to infinity, it gets closer and closer to this dotted line, but never actually touches it. And that is what we call a horizontal asymptote. And that's what this notation, as x goes to infinity, f of x tends to c. It just means that the y values approach a line that they never cross. So the way we determine a horizontal asymptote is 2 cases. The first case is the degree of the numerator is equal to the degree of the denominator. And remember, the degree of a polynomial is the highest power. So in the case of f of x, we have a degree of 2. And in that case, the horizontal asymptote is the ratio of the leading coefficients, which is going to be a 2 and a 5, because those are the numbers with the term of highest degree. So the ratio, the asymptote is the ratio of those coefficients, which again is going to be just y equals 2 divided by 5. For the other case where the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is always y equals 0. So the degree of the numerator is degree 2, and the degree of the denominator is degree 3. So since 3 is larger than 2, this thing, the asymptote is y equals 0. The horizontal asymptote is y equals 0. Always. And we'll talk about what happens when the numerator is larger in a couple of slides. So in this example, we are finding just the horizontal asymptotes. So for f of x, the first f of x, since the 4 is larger than the 3, y equals 0 is the horizontal asymptote. For the second example, we have a degree 2 divided by degree 2. So y equals 9 divided by 6, or 3 divided by 2. That is going to give us 3/2. So that's the horizontal asymptote. And in the case of x cubed over x to the first, we're going to put no horizontal asymptote. And that's going to be because we don't know what happens yet when the degree of the numerator is larger. We do know that we don't get a horizontal asymptote. So a slant asymptote occurs when the degree of the numerator is exactly 1 greater than the degree of the denominator. So here we have a degree 2 polynomial divided by a degree 1 polynomial, and we see the difference between those values is 1. When that happens, we get a slant asymptote, and you get the slant asymptote by doing long division, which we're going to review on the next slide. In case you're wondering, the equation for that line is y equals x plus 1. So y equals x plus 1. That's the slant asymptote. And again, it has to be that this degree is exactly 1 greater. Any more, and we don't get a slant asymptote. You also might see this called an oblique asymptote, but it's the same thing. So for example, 4, we're finding the slant asymptote for 4x squared plus 6x minus 7 divided by 2x plus 3. So of course, the 2 is 1 greater than the power of 1. So we have to do long division. So we're going to have 2x plus 3, and that is going to divide into 4x squared plus 6x minus 7. I don't know why I made the division bar so long. Take some of that out. And all right, so the way we do long division, in case you forgot, you only divide with the term of highest degree in the divisor. So in that case, we're going to be using 2x. So 2x divides into 4x squared. 2 divides into 4 twice. And for the x's, you subtract the exponents. X squared divided by x is going to give you x to the first power. And then just like in elementary school, we just multiply the 2x to both terms. So that's going to give us 4x squared and plus 6x. And of course, then we do the opposite. So that's going to be negative 4x squared and a negative 6x. We add like terms. So that's going to give us 0. And that's going to give us 0. So 2x divides into 0 times. And so our asymptote, our oblique asymptote, or slant asymptote, we're going to say slant asymptote is y equals 2x. That's it. Sometimes there will be a y-intercept that is non-zero. That should come up on the next slide. Oh, is that it? Oh, so that's, oh, sorry. All right, so for this one, it's a self-check. Pause the video and see if you can come up with the domain, x-intercepts, y-intercepts, and any asymptotes or holes for the function. So first, we're going to factor this. So we're going to have x squared, just x minus 5 times x plus 2, and then divided by x plus 2 times x minus 1. And so our domain is, let's write this down. Domain is negative infinity to, let's see, x equals -2, x equals 1. So negative infinity to -2 union -2 to 1 union 1 to infinity. The x-intercepts are the values where the function equals 0 and the fraction equals 0 in the top. So that's going to be when x equals 5 and when x equals -2. Well, x can't be -2, so only x-intercepts we write as points. So that's going to be 5, 0. And our y-intercept is going to be what we get when we substitute 0 in for x. And that's going to be easy to do here. F of 0 is going to equal -10 divided by -2. So we get 5 again. So with 5, 0 and 0, 5. And so we've got domain, x-intercepts, y-intercepts, and any asymptotes. So a vertical asymptote is we get a vertical asymptote at x equals 1. At x equals 1. And we have a horizontal asymptote at, so it's x squared divided by x squared. So 1 over 1 is just going to be at y equals 1. And then our whole is, we have a whole at x equals -2, and that's because the x plus 2 cancels in the numerator and denominator. So we have our domain, x-intercept, y-intercept, vertical and horizontal asymptote, and our whole. And the last self-check is the same thing, but we're finding we have just a different function. So pause the video, come back and check. So for domain, first, always let's factor this. That's going to give us x times x plus 2 times x minus 2. Ooh, the 2 looks terrible. All right, so divided by x plus 3 and x minus 3. So our domain is let's see, from negative infinity to -3, union -3 to 3, union 3 to infinity. That's because x equals -3 and x equals +3. Our x-intercepts are the values where the numerator equals 0. So that's going to be at the point 0, 0. Is going to be at the point -2, 0. And at the point 2, 0, because those are the zeros of the numerator. X-intercepts come from here. The y-intercept is going to be what we get when x is 0. So when x is 0, you're going to have 0 divided by -9, which is also going to be 0. And then we need to find our asymptotes. So we'll say vertical asymptote is going to occur at, we have one at x equals -3. We have another at x equals +3. No horizontal asymptote because the degree of the numerator is 1 more than the degree of the denominator. So that means we have a slant asymptote. And to find that, we're going to do x squared minus 9. And that's going to divide into x cubed plus 0x squared minus 4x, and we'll just do a plus 0 in case we need it. So x squared divides into 3, x squared divides into x cubed, x times x squared is x cubed, x times -9 is -9x. And we change our sign, so that's going to be a negative, that's going to become a positive. So we get 0, and then we get 5x. And so the power x squared is greater than, the power of 2 is greater than here. the power of 1. So we stop a division when that happens. So our slant asymptote is just y equals x. And we do not have any holes in the graph because both of our discontinuities from the denominator are vertical asymptotes. All right, so that concludes our video on introduction to rational functions. We covered domain of a rational function, vertical asymptotes for a rational function, horizontal asymptotes for a rational function, and slant asymptotes for a rational function. Thanks for watching.